As a final closeout to the beam element discussion, I would like to pick up a simple example problem. This example problem is not related to frames, or not the same one as I have worked out in the lecture notes, but just a pure bending beam relation. So the example is given as such. We have a certain fixed condition, support condition, for a cantilever beam at which an end load is acting. So you have here an end load P, and midway through its length there is a support here, a roller support, or basically almost a sort of like a fixed support condition. No, it's just a roller support condition, and the length of the entire beam is given as 2 times L. And yeah, that's all we know about the problem. We know that the properties are such that you have E as the Young's modulus of the material used for making the beam. You have I as the second moment of area. You can call it the moment of inertia, and the rest is given to you. Now these are just pure bending beams. That means you do not have to have any other property. You don't need it, because the beam bending stiffness is just given as EI by L cubed times that entire stiffness matrix, if you remember. So what we need to do is, as in case of every problem, is to start by idealizing the problem. So in case of if you want to idealize the problem, then we know that there will be beam elements which are under pure bending, which means that these are standard beams that we have already done derivation of today. That means they will have 4 total degrees of freedom, and you will have a displacement for the element which will look like n times u, where n will be a 1 by 4 matrix, and u will be a 4 by 1, sorry, and 1 by 4 vector, u will be a 4 by 1 vector, and you'll get your approximate behavior. So that's your idealization. The second case will be then discretization. So in this case, I see that there is a point here where it has been constrained by means of a roller support, and then you have 2 points here, one where it is fixed, the other one where it is loaded. So these are the simplest ones I can pick. So I can say there is an element A and there's an element B. So I have nodes 1, 2 and 3. This is basically now the step of discretization. So I have 2 elements and therefore 3 nodes. If I have 3 nodes, that means if I have 4 degrees of freedom in one element, and there's one node which is shared between the 2 elements, that means in the system the total degrees of freedom are 6. That means UE is equal to n times U, where n is 1 by 6 and u is also 6 by 1. So this is my total. I'm just writing it like that, but you know that the displacement behavior has to be actually defined only for an element, and the rest is just derived or extrapolated from there. Okay, so we can describe all the different degrees of freedom for each element, and therefore set up a displacement vector as well. We also know the boundary conditions of this system already, right? We know that here I'm going to make all the ones that are constrained in blue, so, or gray, or maybe blue is better because you see it. That means I am not allowed to move 2 in this direction. I am not allowed to move 3 in this direction or in this direction. That means I have 3 degrees of freedom that are fixed. So I can name the degrees of freedom for each of the elements. So I can write here element A. So I'm going to make a diagram for it. I have element A here, node 1, node 2. I have UI1. Sorry, we don't have UI1 in that direction, but vertical. So we have UI1. That just is illegible. UI1 and a rotation UI2. Then I have, this is becoming extremely complicated, so I have to write U1, 1, U1, 2. At 2 I have U2, 1 and U2, 2. But I know that U2, 1 is fixed, it's not allowed. And then of course I have forces. So in this case, I have a force acting downwards, which is given as P, and there's no force about the other direction. Here there are, at 2, there are no forces at all, and at 3 as well. Then I'm going to write here the diagram for element B, and I know I have node 2 that is shared, and you have these two, and we already know this one is fixed, and here we have U31 and U32, and both of them are going to be fixed. And of course there are no loads acting, there will only be a reaction which will act at node 3, and there will be a vertical reaction at node 2. Now, so we've idealized this, we've discretized it, we also know what kinds of boundary conditions and loads are acting on it, so the whole problem is quite nicely defined. Now we need to set up the equilibrium equation, which is basically K U is equal to F. This is for global, of course. Now we want to write down for the global system of the two elements. Both of them are lying in the global coordinate plane, so we don't need to do any transformations. And one of the reasons why I picked this problem is that we don't need to do any transformation, so it's easier to do it on this one slide. So as a building block, we already have the description of of a simple beam element, right? So just for memory's sake, I can write K for a single element is given as EI by L cubed, 12 6L minus 12 6L, because L is also the length coincidentally of each of the element if the total length is given as 2L. And I'm going to fill up all the details like I've done for the rest of the videos today. You can of course forward this part if you don't want to watch me write, and if you are writing with me, then I'm extremely happy to hear that or see that, because I really hope you are working out all the problems as I do to get some bit of practice. So this is my basic building block for every element. Now I know that this is my building block for element 1 or element A, and I can write the same building block for element B as well. And in this case for element A, I have U11, U12 dependencies, U21, U22. The same way in the rows, it's exactly the same order. I'm going to write it for element B. It's exactly the same stiffness matrix. So if this video is getting a bit too boring and too long, I apologize already in advance. Or maybe it gives you a bit of time to catch up with the writing. Here too, I'm going to write the degree of freedom dependency. So it's going to be U21, U22, U31, U32. And the same exact for the rows, U32. Now, as I've shown you before also for trusses, if you have to find the common terms in both the matrices, it's quite easy. You have to see which ones are common. We know that in this problem, there's only one node which is common, which is node 2. So you can quite easily pick up all the commonalities from node 2 and put them in a global matrix. So if you see here, I have everything related to 2, 2, which is going to overlap from here, and the same over here. So you'll basically have to add up these two parts. So if I'm going to start writing a global stiffness matrix, so U11, U12, U21, U22, U31, U32. Sorry about this, but I'm a bit cramped. I should have planned better. So I'm going to set up a matrix which you can see is 6 by 6 for 6 degrees of freedom. Of course, this matrix is going to be multiplied by EI by L cubed. Not important right now, but I want to show you how I'm going to assemble everything together. So you know that here I have everything only related to UI1 and UI2, and also relation of UI1 with UI2. So this is something that might be important. So everything in this row is UI1, U11 and U12, which is not going to repeat anywhere else. So basically we can just copy these terms here. This could be improved a little bit. Yep. So you can write here 12, 6L, minus 12, 6L. Now we know that with the node 3, there are no contributions, so there will be zeros. Same way for U12, we will copy in everything that is befitting. So U1 and U2 node matches, and with 3, 1 has nothing. Then with U21, that's where the fun begins. So you have contributions of U21 with U11. So you see U21 with U11. So you have here is with node 1 and 2. So you can write here minus 12 and minus 6L. Now with U21, we see that there are double contributions in both the elements. So you have one contribution here and you have another one over here. So these two need to be added up. That means here we will get double terms. That's going to be 12 plus 12. So we can write here 24. And the same with U22. With U21, so you have 6L and minus 6L. That means if I add it up, I should get 0. So I have 0. And with 3 and 2, there's only single contribution, so I can just copy minus 12 and 6L. Now I do the same with U22. So with U22 and U11, there's only one contribution, so I will have 6L, and then the same with U12. And when it comes to U21 with U22, I have two contributions, minus 6 and 6L, which also add up to give me 0. And the next one, U22 with U22, is 4L square in both the matrices. So I add it up and I get 8L square. And the rest remain the same. So that's minus 6L, 2L square for U22. Now U31 is has only contributions with node 2 and 3. So all the contributions with node 1 have to be 0, and the rest we can just copy the terms from the stiffness matrix that fall under the right set. That's our final global stiffness matrix. K, you can write it as global AB is equal to. So this is our final matrix, and this is where all the contribution of the common nodes went in, and the rest remained the same. Now if I write this stiffness matrix KGAB times U is equal to F, then I will be able to solve it for the unknown, because AB is now known to me. I'm not going to write out that humongous matrix, but I'm going to write out the displacement vector. The displacement vector is exactly what we have been writing before: U11, U12, U21, U22, U31, and U32 is equal to forces, which is F11, F12, F21, F22, F31, F32. Now you know that in this there was no distributed load, so therefore we don't need to derive the load at every node. And there was only one load that is acting in the system, and that was acting at node 1 in the direction of U11 negative. So we can go back here. This becomes minus P, and the rest are zeros. So this is my new force vector. Now we also know that according to the degrees of freedom that are fixed or constrained, we can get rid of 3 degrees of freedom. One is at U direction, it's not allowed to move in the Y direction, no transverse displacement, and at node 3 both the displacements are fixed. So what we have left is U11, U12, U22. So if I go back now to the stiffness matrix here, then I can remove the rows and columns that actually correspond to the displacements that are fixed. And that are U21, so the one that is related to U21 can go away, the one related to U31 and U32. So all these rows and columns can be reduced, and what we have left are then three sets of equations, 1, 2 and 3, to give you the three unknown degrees of freedom, which are U11, U12, U22, and this vector is also defined. So your unknown degrees of freedom U11, U12, U22 will be given to you as results. So I would like you to work this out and give me a solution as to how it ends up for you. There are also simpler ways of calculating it by means of analytical terms, so you could also do that to check or verify whether your results are correct or not. Using these results, you will also be able to set up a force moment diagram on the beam, a shear force diagram, and of course a bending moment diagram. So if you are up to it, please go ahead, finish this up to the bending moment diagram and discuss the results on the discussion board or in the classroom next time. I'll be more than willing to have a look at it and discuss it with the rest of your peers as well.